Okay, I'll make a slow start just to introduce Tom, and as people still sort of coming in. So hi everyone, welcome to another one of these HSMA showcase sessions. As I say, the idea of these really is to give you, first of all, to give you a bit of a flavour of what the PenCHORD team do beyond teaching you weird stuff in HSMA. We do research. We're a research team, so to give you a bit of a flavour for that kind of stuff. But also, obviously, over the coming months, you're going to be increasingly thinking about your project work. What your project ideas might look like, and obviously you're now getting exposed to huge numbers of various methods that you can use for this kind of stuff. So some of these ideas, some of the things you'll hear about within these showcase sessions, to give you a bit of an idea about how some of these projects can work in the real world, how you can do some applied and impactful modelling and data science in health, and so hopefully these will help to spur some ideas and other things that you might want to consider when you are putting together your project ideas. So we've had a couple already. Obviously, I gave the first one back at the start around some of the end-of-life care modelling I did, and then we had a few weeks back Anna and Mike who talked about the huge Samuel project and the machine learning work that's going on, a big part of what we do in our team. But today, really grateful that my colleague Tom has come along to talk about some work that Tom and Mike did right at the very start of the pandemic, looking at the provision for dialysis patients, particularly vulnerable groups. So without further ado, I've hit record, I've remembered to do everything. I will hand over now to Tom.
Thanks, Dan, and welcome everyone. It's great to be here to give you a short talk. And I think hopefully you'll find it useful, particularly from a kind of practical perspective, because the tools and methods that we used within this project are all related to what you've been learning about in HSMA. So I'm going to just try and share my screen, make sure I share the right one. Dan, can I just check you can see my maximized slides?
Yeah, that's coming through okay.
Excellent. Okay. Yeah, so as Dan said, this was work, actually it was with the Wessex Kidney Centre, to do with organising their service at the start of the pandemic, really to assess the robustness of that service and what sort of problems they might face in worst case scenarios or medium case scenarios for COVID. I just want to give some credits at the start of this talk to colleagues that I worked with on the project. So Mike Allen is somebody you've already met. He's a senior health data scientist within PenCHORD. Mike did the simulation modelling, or most of the simulation modelling in this project with me. Martin Pitt is the director of PenCHORD, who you may or may not have met. So Martin was involved, along with Stuart Logan, who's the director of PenArc, in the sort of setup of this project and what we should do. And then from the Wessex Kidney Centre, there was Amir Banji, Jonas Williamson, and Stephen Dudfield, who were the NHS colleagues that we collaborated with quite closely all the way through. Of what you'll see is a relatively short piece of work. So if you're interested, there's some research materials to go along with this that you can take a look at. So there's a paper in PLOS One called the same as this talk, a simulation modelling toolkit for organising outpatient dialysis services during the pandemic. There's a bit.ly link there. The first link will take you to it. But also all the code that we wrote is available on the University of Exeter GitLab. I forget why we use the University of Exeter GitLab over GitHub. It was a crazy time. It's what we did, but feel free to check that out. I think we've set it up to work with Binder as well. So you better run that online without installing anything on your own machine. That's what you wish to do. And then for a bit of general background on how simulation modeling might help with these types of problems in general, me and some colleagues very early on in the pandemic also wrote this paper, how simulation modeling can help reduce the impact of COVID-19, led by Christine Curry from Southampton. And there's a bit.ly link there to check that out as well. And that talks in much more general terms if that's what you're interested in. So a bit of background to this project. So it was very early in the pandemic, right at the start. So it was mid-March, really, 2020, when I think I've got the exact date somewhere, when we were approached by the NHS. They substantially stepped up their planning for kind of what was fast realizing it was going to be a bad situation for quite some time. But at this stage, don't know if people remember, the view was that 80% of the population would be infected over a 3 to 6 month period in the worst case scenario, which kind of seems almost crazy now when we think about it, but that's what we were planning to at that point. It was, like I say, it was right at the start, so only just beginning to social distance. But of course, there was this group of vulnerable patients that required dialysis who can't social distance all the time because they need to interact with the NHS. They are outpatients. They need to come in for their treatment, very important treatment. And some of those patients would become infected, either outside of the hospital or within, and then they needed to be separated in some way from the uninfected patients. You probably know all this, but I'll briefly just mention dialysis. So it's to do with, it's a renal issue. It's to do with kidneys that are required to filter the blood and really just removing harmful waste products from them. If you don't get dialysis, it becomes quite painful and unpleasant. So really, reducing their treatment wasn't really an option at this point. So we were trying to find a way to protect this vulnerable group through service reorganisation. If you've never seen a dialysis suite, I think this one is somewhere in the Midlands. I won't say where, but this is a very nice looking dialysis suite. So you have a chair, and importantly, you have these machines that you need to go and use. So this was at the Wessex Kidney Centre. If you don't know where Wessex is, you can be forgiven. It's this red square here where we've got Salisbury, Basingstoke, Winchester, Portsmouth, Southampton, all grouped together. So Hampshire, Isle of Wight, a bit of Wiltshire, all grouped together. If we zoom in on that, this is a map that Mike Allen generated very quickly using, I think, GeoPandas on the first time we spoke to the NHS about their problem. So what we have here are stars, and they represent centres that deliver dialysis. So there's dialysis suites at each of these centres. And then the red dots represent where patients are located. The bigger the circle, the more patients are located at that particular place. So as you can see, it's a geographic problem we needed to deal with. And some of those patients are located quite remotely from the centres, and they need to travel in order to have their service. Overall, there was about 650 patients in this population. That remains fairly static over time. About 2/3 of those vulnerable patients require some form of transport to be provided for them, typically through the ambulance service, the South Central Ambulance Service. So the plan here was to try and figure out how to separate infected and uninfected patients in a way so the service could still deliver the same level of service to patients. So one option they were discussing was a COVID-19 ambulance, so a special ambulance that would transport one infected patient at a time. And there were serious questions around how feasible it was to do that with the size of their population. Another option was to centralise outpatient dialysis for infected patients to the largest site, which is Portsmouth. That's the biggest site in Wessex. Okay, so infected patients would all go to that one centre, and that would potentially displace them, and it would also displace patients who were already using Portsmouth because it would start to use up the capacity at that location. And you could separate them not just by place, but also by time. So you could split the use of the room up into shifts. So there was a shift where, so for example, the morning would be used for infected patients and the afternoon for uninfected patients, or vice versa. And they also were considering building a wall, so a perspex wall that went down the middle of the dialysis unit to physically separate infected patients from uninfected patients. Drastic measures. So our research questions were, and our aims were, to stress test the plans that they were coming up with under a whole, because of all the uncertainty, we had no idea what was going to happen at this point, under a range of scenarios. So that means we were going to look at from the worst case scenario through to some moderate scenarios and see, do their plans stack up against that? We were interested in what happened to both the outpatient workload and the inpatient workload over time. So were certain units stressed? Was there an overflow to a secondary site, etc.? Were there plans for patient transport feasible? So was this ambulance idea of transporting a single infected patient at a time feasible or not? And also, if instead of having a single patient being transported, could we transport more than one infected patient at a time? And what was the kind of benefit of doing that in terms of overall time travelled? And what we wanted to do was develop tools that in theory could be used by any dialysis service in the UK or elsewhere, and publish those so that they were available for others to use. I always say in theory, because until you come to actually reuse these things, you never really know if it's going to stack up or not. With the added problem that we needed to do this really within 2 weeks. So what actually happened? So here we go, a date as promised. So we were contacted on the 18th of March 2020. We had an initial Zoom meeting on the 20th to scope out the work. We kind of blisteringly, unbelievably received data within the hour for us to start our analysis. So that is highly unusual for a research institution. So we had anonymized data almost instantaneously. And that, for example, Mike produced that map within another hour of receiving that data and got it back to the NHS. So we agreed that we would do some modelling pretty much night and day for the first week to make sure we had some results, which we did. But we realised that actually these weren't the same. Our objectives didn't have the same model. There were two modelling projects here. One was kind of a simulation of the network of sites and workload across them, and the other was separating out this travel time problem to do with ambulances. So that was quite challenging within the time frame we had. So we needed to meet with the NHS every day or every couple of days, and sometimes that was both me and Mike, and sometimes it was just one of us. And so yeah, so we managed to do all this within 2 weeks and some quite late nights of modelling. It's worth saying that me and Mike have been kind of modellers in this area for, well, between us we've got several decades worth of experience. So we weren't walking into this sort of thing completely blind and having to learn everything from scratch. So you've been learning about using SymPy in HSMA. So the first thing we did was we used SymPy and we built a discrete event simulation model of the dialysis network. We separated out the transport problem and we used a bit of simulation there, so a bit of sampling for patient populations, but also these things called meta-heuristics to model transport. And that was really about finding good routes, optimal routes to try and get an idea of what routes the ambulances would take. I'll talk a little bit more about that in a moment. And with both of those, we used scenarios to handle the uncertainty about the spread of COVID-19. So the simulation model was kind of a mix of operational and progression of patients through a susceptible, infected, recovered, classic epidemiological model. So the dialysis model was run for a year and it simulated their progression, outpatient patients' progression through being negative, contracting COVID-19, and that was a kind of a scenario input. And then they'd remain in that state for kind of a stochastic amount of time, so a variable amount of time. And we would sample that from one or more distributions that we had defined. Some of those patients would recover, no problem, and they would carry on being an outpatient. A proportion of those would become inpatients, and they would require inpatient care at Portsmouth, for example. And then they would kind of recover from that, and they would go back to being an outpatient. But we also had a parameter looking at what patients might pass away, and we pulled that from early literature about COVID-19 and dialysis patients. So here's an example of the sort of outputs that simulation model could produce. So it's worth saying that this is a network model. So we modeled multiple sites at the same time. So on the right here, we have, for example, BST is Basingstoke, HU for whatever reason is Portsmouth. So that's the place where most patients were going to. And then plotted on these charts are the numbers of patients in different states within the model. So what you can see is these thicker lines, and they're the average of multiple runs of the model. So for example, we can see negative patients gradually drops over time and then levels off after day 100. And in black, we've got all the positive patients, and that sort of peaks here, I think around about 125 after about 70 days and then drops off again. But we can break that down into, for example, outpatients and inpatients in red and beige, gold, something like that. You can see these lines either side of it, and that's just kind of the limits that we've seen within the multiple runs of the model. So it's not the full uncertainty with this type of modeling. We handled that with scenarios, but it just gives a little bit of within scenario uncertainty. So here's an example result that we got with the model. This is Portsmouth here. We can see, so first of all, you see in all the other places, the number of patients negative drops off, and that's because they're contracting COVID-19 and the model is rerouting them to the centralized site at Portsmouth. And at Portsmouth, we see a growth in both the positive outpatient population and the positive inpatient population here. Now, it gets to a point after around 60 days where Portsmouth no longer has sufficient capacity for those outpatients. And so we have a secondary site where those patients are rerouted to, which is Basingstoke. Okay, so that was a first finding, was that actually, with the plans that they had, in the worst case scenario, there would be an overflow to Basingstoke, potentially after around 2 months. So the patient transport problem. So a little bit more complicated than that. Let's say we've got these group of patients, we need to pick them up and route them to hospital. So in the academic literature, we would treat this problem as what's called a dial-a-ride problem. So there's a set of customers, and they need to be picked up and delivered somewhere, in this case, to a scheduled appointment at a hospital. The ambulance that's picking them up has a given capacity, and the appointment has a time. There's a time window in which they need to be picked up and dropped off at their appointment. And normally you have a constraint around the maximum ride time that you would allow. So you wouldn't allow the ambulance to drive around all day picking up patients. Now, that's a very complicated problem, and it's often used in the context of scheduling, so routing and scheduling. So you would define a model that is used on an ongoing basis that would help a service plan for picking up their patients, for example. Now, we didn't have any data on appointments. That wasn't available to us in the time we had. And we also had a whole huge amount of pandemic uncertainty that these dial-a-ride problems aren't really set up to deal with. And also, while we were thinking about this, we realised that the NHS didn't need routine support here. What they needed was just a rough idea of would their current plans succeed or not. So because of that, we simplified the analysis into what we call the capacitated vehicle routing problem, which is a much more simple problem to solve analytically and computationally. So this is just a simple example here. So we have a hospital, let's say, where an ambulance is located to start off with, and we have a set of geographically located patients. Okay, and that vehicle has a capacity. Let's say it can hold 4 patients at this point. So what the capacitated vehicle routing problem does is it finds the minimum number of routes that reduces the overall either drive time or driving distance. So you can see here on the right, it's constructed a series of routes to pick up those patients and then return them to the hub or the hospital or whatever you want to call it. So how did we set this up? Well, the first thing we did was we used the network model to generate estimates of patients that had COVID-19 at any given point. And then we used simulation to sample roughly that number of patients geographically located within that population. So we ran the model many times, and each time we sampled a handful of patients who had COVID-19, and they would come from the geographic spread that we saw in the real data. And then we constructed a series of routes. So we did that using something called the Clark-Wright savings algorithm. Okay, so that's a classic vehicle routing algorithm that's really kind of straightforward, almost like a rule of thumb. And that gave us an initial solution, and we did that in parallel to speed things up. From that initial solution, we used a full-blown meta-heuristic to gradually improve on those routes. And remember, all of this is really, it sounds technical, but really it's just about constructing what is a feasible route that would give the NHS a rough idea of what sort of travel time implications there would be for different capacities of vehicles. So we used a classic meta-heuristic called the iterated local search. So much more computationally intensive than Clark-Wright savings, but a very well-known, well-trusted algorithm. And we implemented all of this in Python and NumPy. So we do that many times. Okay, so simulation combined with heuristics. So each time we run the model, we sample a bunch of patients who have COVID-19, and they're from our geographic spread. And then we gradually produce a set of routes using these computational methods that gives us a rough idea of how far they would travel and for how long. And then we do that again and again, and we can look at the distribution of results that we get. And it gives you something like this. So here we've got a box and whisker plot looking at, sorry, I've not labeled the axis, that's bad practice, but let's say it's travel time, total travel time, and how that reduces if you increase the capacity of the vehicle. The message here is really simple. If you're going to have an ambulance that picks up only 1 patient at a time from quite a large area in Wessex and returns those to a hospital, it's just not going to work. But you can save up to 50% or 60% of that by increasing the capacity up to 4. But even then, that's a very large amount of time that's going to, one ambulance just really can't cope with that. So they needed another plan. So just to give you some broad findings of the study overall before I finish up. So really one of the findings was if the current outpatient capacity was maintained, the dialysis unit network should be able to cope with the worst case scenario of rapid 3-month spread of COVID. So yes, there would be some spillover, and yes, that was extra information, but there wouldn't be a complete disaster, which was what they wanted to check for. Yep. And then inpatient capacity. So I didn't really talk about that, but the inpatient capacity at that one site, we found it would be breached. Okay, so they would have dialysis patients who would effectively become outliers on other wards because they had so many with COVID-19. And then lastly, as I alluded to in a bit of detail, the transport plan that they had wasn't going to work, and they needed to rethink that pretty rapidly. So one option was to kind of temporarily relocate patients closer to treatment facilities. That's what they were discussing at the time. I think the plan was, in the end, they had to pay for lots of taxis to pick people up. So yeah, a bit of feedback at the end. So, we don't want to blow our own trumpet too much here, but basically it was helpful for them because it was quick. Okay, because we were able to produce these models in Python quickly, it enabled them to adapt their plans as they went along. And that's very much what we saw happening as we were working with the NHS. And for us as academics, that's really great. That's much better than doing research. And what we're interested in particularly in PenCHORD, is making an impact with our research. And I think this type of applied work is the way to do that. So yeah, so that's it from me. I'll hand back to Dan. Maybe there's a few questions, but just to say that if you're interested in the code in this, I've given the link here again at the bottom. Feel free to go and have a look at the simulation. Might be particularly interesting to you that Mike and I put together.
Brilliant. Thank you very much, Tom. So yeah, any questions for Tom about any of that? Yeah, Duncan.
Oh, sorry, I didn't actually have a question. I was just giving a round of applause. Looks like really good work.
There it is. Anybody else? Oh, yeah, got a question. Hand up. I hope that's a hand this time.
Hi, Thomas. I was going to ask. This is a more technical question. I'm enrolled on the program with Dan, and my background is on health economics. And sounds more like, so you had like two things going on at the same time. I don't know whether I understood well. So one is the health status of the patient may vary, and the other, and that will feed in then into SymPy, so from run to run. Is that right? Because usually we think in terms like of Markov models, in terms of how the health status moves from one state to the other. Was that the way? Am I thinking along the right lines or not?
Yeah, so that's a good line of thinking. That's quite similar. So we had an individual level model with discrete event simulation. So we had individual patients in the model instead of a cohort of patients. Yeah. So there's a progression part of that. So the patients were progressing through the stages of COVID. But there was also an operational part, and the operational part was really here about which units would take those patients, where would they go to, and trying to find the right one for them, and then what were the implications for other patients there? Were they then displaced elsewhere within the network? So we had a set of simple rules that effectively decided where the patients would be routed to within the network. If you have a look at the paper that I linked to, there's a section called Unit Search Strategy, and that describes that in detail.
Okay. Thank you. Thank you.
You're welcome.
Any other questions, sorry, for Tom? No. Okay. In which case, I'll thanks to you, Tom, again for
pleasure.
Yeah, really interesting talk. And I think, as you say, particularly given with the HSMA's not long learned SymPy, I think is a really nice demonstration of that aspect. And of course, Elliot's going to be taking them through geographic modelling after Christmas as well. So a nice introduction to some of the power of that too. So yeah, I'd encourage you all to check out the links that Tom shared, and we will of course put this recording up on YouTube as well, so you can watch that back at your leisure. Brilliant. Thanks you very much.
Thanks everyone. Bye-bye.
Thanks everyone. Bye-bye.
Thank you.
Thank you.